Hey everyone, Connor here from the Gitcoin team. We're here for another workshop for the Cross-Chain Hackathon, this time with Cosmos about IBC. And so we have Christopher Goes. Am I saying it right? Just Goes?
Yep.
Christopher Goes to talk about Interchain GmbH. And like I said, if you have any questions, drop them in the chat. We can potentially unmute you. We'd love to kind of make this a open discussion. So without further ado, Chris, let's take it away.
Thanks. So I'm not going to talk too much about Interchain GmbH. I just work at Interchain GmbH. The interesting subject of this presentation is the IBC protocol, which is, of course, the subject of challenges in the ongoing hackathon, of which I assume you are aware if you were in the Zoom call. Thanks again for joining. So what am I going to talk about in this workshop? There's like a 2-second delay on these slides. It's super strange. Okay, anyway, I'm going to go over briefly some of the hard problems in cross-shard and cross-chain communications, which I think are common to cross-shard, cross-chain. They're really much the same problem. I'll give an introduction to the IBC protocol. If you attended the live stream last Friday, there will be a little bit of overlap, so apologies for that, but there will also be some new content. I'll go over which of these hard problems the IBC protocol tries to solve, which of these problems it doesn't try to solve, and how you could solve those problems sort of building on top of it or building with it as a component. And I'll talk, of course, about the constituent parts of the IBC protocol, what abstractions are used, how they need to be instantiated, how they fit together, what security properties they need to have, and how you as a developer can utilize them. I will then take a quick pause to answer any questions. Also, feel free to interrupt me at any time in the middle of the presentation. I want this to be as interactive a workshop as possible. Of course, you'll need to be unmuted, but we can do that. But I'll also, after I give an introduction, pause specifically for questions. Then I'll give a brief overview of how you can dive into the code, what repositories do which at the moment, where you can find them, and what you need to know to get started using IBC in your application. Does that sound good?
Sounds good to me.
Cool. So, what are some of the hard problems in cross-shard and cross-chain communications? One hard problem is transport. Transport simply means getting data to the right place. Imagine you have lots of shards or lots of blockchains. All of those shards and blockchains are doing lots of independent processing, and you need to get data from one shard to another. Of course, you're limited in how you can do this because blockchains are not computers. They can't make non-deterministic HTTP requests over network connections. So you need some method of physical data transport to figure out that, oh, shard A wants to send data to shard B, chain 1 wants to send data to chain 2, and just transport that data to the right place. One hard problem. Hard problem number 2, authentication. Even if you've transported the data, it could be the wrong data. Blockchains are public, anyone can submit transactions. If you just accept incoming messages without authenticating them, you won't have secure communication systems at all. So hard problem 2 is authentication. The chains of the shards need to be able to check somehow that data they're getting, and here we're just talking about data in the abstract. Think messages, byte strings, could be anything. They need to be able to check that it is in fact the right data. That if shard B receives a message from shard A, it is actually a message that shard A sent, not a message that shard C sent, not a message that some other chain sent, not a message that no chain sent at all, but that was just forged, etc. Hard problem number 3, ordering. If you've got transport and authentication, you can send messages and you know that they're authentic, that they were actually sent when you receive them. But you can't reason about much because you don't know anything about the ordering of these messages. You might have messages completely out of order, messages from a year ago, messages potentially from the future, messages that aren't, you can't reason about any sort of composite state guarantees where you want to think, oh, I have a dApp that has state on multiple chains, multiple shards. What is, are tokens conserved? Are NFTs only owned by one person at once? Can I reason about the invariance which the gestalt state on multiple shards or multiple chains maintains? And in order to reason about that, you really need to be able to reason about the order of message delivery. So hard problem number 3 is ordering. Hard problem number 4, I'm just going to call the general class of state dependence or atomicity. So this generally requires ordering, like I talked about, but then you might have further cases where you want certain things to happen atomically. So you want to reserve, I think the classic one is called the train and hotel problem. You want to reserve a train in a hotel because you're going, I guess this is a example from the pre-coronavirus world. We need a new one for the post-coronavirus. Or let's say you want to, schedule a Zoom meeting with some friends atomically, and if your friends start agreeing to a time and you didn't agree to that time, then you might agree to different times. So somehow you want to all atomically agree to the same Zoom meeting time at once. But if you're all using different shards of some calendar blockchain, I realize this example is a stretch, y'all are using some shards of a calendar blockchain to schedule this meeting, then of course you need the ability to somehow atomically choose the same time, or atomically book a train and hotel for the same trip. So hard problem number 4, state dependence, atomicity. Hard problem number 5, denial of service resistance. In the setting which we consider in IBC, and most of the settings which are considered in cross-chain and cross-chain communications, the blockchains are public, meaning that anyone can submit transactions, anyone can try to send messages, which may or may not authenticate, but of course, these ledgers need to be denial of service resistant. So whatever we do for transport authentication, ordering, atomicity needs to be denial of service resistant. It needs to be metered by gas, metered by some other mechanism, such that it can't just be spammed. Hard problem number 6, dynamic topologies. This then starts to get into the nitty-gritty of what specific kind of cross-short or cross-chain communication problem you're talking about. IBC takes the most general formulation of the problem, where the topology of the chains or of the shards itself is dynamic. So whether there might be new chains coming online, chains going offline, chains upgrading, chains changing their validator set all of the time and independently. So there are no a priori guarantees about what the structure, what the topology of the network of chains looks like. So in some cases, this problem is simpler. If you have a master chain, basically like ETH2 or like Polkadot, a master chain which always knows what the shards are or assigns validators to them, or you could even have a simpler system where you just have 16 shards, period, and it never changes, then you can make more assumptions here, which simplifies the problem. But in full generality, you want to deal with a dynamic topology. And then hard problem, let's see, I'm up to number 7, is load balancing. So if you have lots and lots of shards, that's great. You have lots of throughput or lots of chains, maybe with some specialized chains for different applications, so throughput. But of course, if you end up sending all the transactions, routing all the transactions, putting all the popular dApps on the same shard or chain, that won't do much for you because you'll have all this unused throughput that you're not actually using. So this is dependent, of course, on the application which you're considering, but you need some way to load balance, to split compute and storage load, perhaps according to particular proclivities of particular chains across chains of shards. All right, a list of hard problems. Then, which of these hard problems does IBC actually try to solve? It would be very, very ambitious. We think a little bit too ambitious to try to solve all the hard problems at once in a single protocol. That would be like the cathedral approach to software development, I suppose, where you try to build, one operating system that does everything for everybody. And that, it's like the Windows approach. We're much less about that. We're much more about the Linux approach. So IBC tries to solve a small subset, or a medium-sized subset of these problems that we think go nicely together in one protocol, and then intends to allow users to use IBC to build further protocols. This is also inspired by the design philosophy of the TCP/IP SSL/TLS stack. So if you consider the web stack, which runs the modern web, which despite later on monopoly power acquired by ISPs and acquired by platform companies, the fundamental architecture of the web is quite decentralized. There aren't central points of failure, and it, at least so far, has continued to hold up during this pandemic, which is a good, I suppose, demonstrator of its flexibility or fault tolerance. So IBC similarly is designed to serve as a component that solves some of these problems, perhaps solves enough of the problems for simple applications, but that can be used to build more complex protocols to solve perhaps more complex application-specific requirements. IBC solves transport, meaning that it deals with what it is to transport data from one chain of shard to another chain of shard. It solves authentication, what it is to authenticate data to ensure that it came from the place where it says that it came from. It solves ordering, allowing you to reason about the order in which packets were sent when you receive them. It deals with fully dynamic topologies. We want to treat this case in full generality, so IBC supports a set of chains of shards where they're coming online, coming offline, and no central party even knows what they are. No single party may know all of them at once. And it deals finally with heterogeneous chains and consensus algorithms. IBC does not solve natively denial of service resistance, so it assumes that there's some kind of IBC is basically a protocol that blockchains can implement, so it assumes that there's some kind of denial of service resistance, like gas metering on the chains, or that's further considered by applications which use it. IBC itself does not solve atomicity. It provides primitives like ordering and authentication that you can use to build more complex, say, atomic commit protocols. But IBC itself does not do that. It does not solve load balancing, and it does not deal at the moment with forks or rollbacks. It assumes finality. This makes the problem much simpler, and it is, of course, simulable with some degree of configurable risk by choosing some confirmation threshold for Nakamoto consensus chains like Bitcoin or Ethereum. If you're using Tendermint or using Grandpa, which is Polkadot's finality gadget, or using some sort of other BFT system, you will have finality. A few myths that I want to quickly debunk, just because they are often held. IBC is not Cosmos specific. It's not specific to the Cosmos Hub blockchain. The Cosmos Hub blockchain will support IBC, but it has no special control over it. You could use IBC and talk to the Cosmos Hub. You can use IBC and not talk to the Cosmos Hub. You can use IBC and do whatever you want. It's just an open source protocol. Another myth, because I think the original example in the Cosmos white paper concerned token transfers. IBC is not just about token transfers. In fact, the core protocol, which is what we've spent most of our time working on, is completely agnostic to the application use case. So you can use IBC for, I'll get into some specific examples later. You can use it for token transfers. You can use it for cross-chain voting, cross-chain transactions. You can use it for things which look like sharding, where you're passing code around. IBC, the core IBC protocol, is completely agnostic to what you are doing with it, what the data semantics are at the application layer. So I want to take a quick pause. Any questions so far? Did those problems make sense? Does the scope of what IBC intends to accomplish make sense?
Makes sense to me. We don't have any questions in the chat yet, but if there are any, please post them, or I can unmute you if anyone is interested.
Cool. So now I'll dive in a little bit to the abstractions which IBC uses. Just a note, in case these sound too scary, it's possible to use IBC as an application developer without understanding all of the internals. Just like it's possible to write a website now without understanding exactly how HTTP works, or it's possible to use HTTP without understanding how the entire low-level router ICMP IP stack works. In this analogy, IBC at the moment is at the level of the lower TCP IP stack, and if you're writing an application protocol on top of it, you will be writing something that looks like HTTP. But to write HTTP, you don't need to understand all of the internals. It's helpful, and they're interesting, and they're not too complex, so I'm going to go over them, but just a note that it's not required. So what does the IBC protocol stack look like? Clients, connections, channels, packets, modules. And I'm going to go through these in order. Clients. Clients serve the purpose of verifying consensus transcripts. So here, when I describe, actually to go back, just back a slide, when I describe all of these are abstractions. So these are specific interfaces and sets of rules and some logic that IBC defines. And then parts of these interfaces can be instantiated by different specific algorithms. So in the case of clients, clients serve the purpose of verifying consensus transcripts to authenticate data. These are basically like clients, but of course in the IBC context, so instead of running on a phone, they're running on a blockchain in the state machine. And the client abstraction in IBC is defined in a way such that it can support any consensus algorithm with a finality that can be verified. Now, the cost might vary. You might have more efficient light clients, less efficient light clients, but as long as you can verify a particular state, say at a particular block height of what the blockchain is committed to, it can work with IBC. And the algorithm which defines how to verify that will be integrated into what's called an IBC client. So when you connect two blockchains, the first thing you need to do is create a client on one chain for the other chain and create a client on the other chain for the first chain. Connections. So now we have clients, but clients only allow you to authenticate data. They don't do any sort of pairing. And reminder that we're dealing with a dynamic topology here, so we have lots of blockchains changing all the time. If we want the ability to send messages between just two chains, we don't want the messages to go anywhere else, we need a way to associate the chains. So the way to associate the chains we call a connection. And a connection is, say, if you have two chains A and B, you run what's called a handshake protocol to set up a connection, which basically sends some control messages between the two chains. Both chains agree that they want to have this connection. They agree that it's going to refer to the other chain. They check that, and then they end up with a connection, which both chains can use to refer to each other uniquely. Now, just a connection isn't so useful because on top of these chains, we expect our running modules. I'll get to what modules are precisely in a second, but just think of modules as units of code. So in order to send actual packets, in order to send the interesting bits, you need to establish a further pairing between modules. So modules like could be a smart contract on Ethereum or a SDK module on Cosmos, for example. And a channel is a data pipe between two modules on two different chains. So you also use a handshake to set this up, and in the handshake you can negotiate a kind of protocol version. But once you have a channel set up, you can then use it to talk between the two modules. So to dive a little bit more into the definition of a module, we want in IBC to deal with the case of separated, permissioned, not permissioned, but units of code with separate permissions, usually over storage, and usually with separate compute logic. So in the case, this is like a general definition, but in the case of Ethereum, these would be smart contracts, where smart contracts have isolated storage and they have a particular contract code, which is fixed when they are deployed. In the case of Cosmos chains or the Cosmos SDK, these will be Cosmos SDK modules, which have separate store keys that they can use to access their own stores, which no other modules can access. In the case of Substrate, I think it's also called modules, similar abstraction. Most smart contract blockchains or most blockchain frameworks are going to have a abstraction that looks like this. And in IBC, we kind of call this a module. And we assume that modules don't trust each other. So just like you don't trust all of the other smart contracts on Ethereum, when you deploy an Ethereum contract, you trust maybe your own and only a few specific others where you've read the code. Likewise, in the case of IBC, we want you to only need to trust a few specific modules on the other chain that you want to communicate with. So then you set up a channel between your module and the other module which you want to talk to. Once you set up a channel, you finally are ready to do the interesting thing, which is to send and receive packets. So packets are where all the action is at. Now notice that I have not yet talked at all about what specifically the application is doing. And that is because the core IBC protocol, the TAO or Tau of IBC, does not care. The Tau of IBC is just responsible for transporting, authenticating, and ordering packets, getting them where they need to go, making sure they don't go anywhere else, making sure they are always addressed correctly, decoded correctly, etc. But what those packets contain, what their semantics are, whether they're for token transfers or voting or sending code around, IBC doesn't care, it doesn't even know. It can't reason about them at all. They're opaque to it. Just like when you open a socket using the TCP/IP protocol, you send byte strings, and the lower levels of the protocol don't care what they mean. They're just responsible for getting the byte strings from one place to another. IBC works the same way. So finally, not quite an abstraction, but I just want to mention it because it's an essential component. We need some additional off-chain process to perform the physical data transport. So all of the authentication logic, handshake logic, ordering logic, all of that logic can be executed in the state machines of the chains themselves, in a smart contract or in a module. But of course, chains can't make HTTP requests. We need some way to get the physical data, some way to transport the data from one chain to another. And the process which is responsible for this we call a relayer. A relayer is not permissioned. They don't need to sign anything. They don't, They're not authenticating anything. You don't need to trust the relayer. Anyone can do it. But they are just required to perform physical data transport. And who is serving as the relayer is probably going to vary based on the application. Any questions? Then I'll run through this diagram. Looks like these have been answered.
Yep, we handled the contact. I guess real quick, is there any way you'd like people to contact you if they have specific questions after this call?
Yeah, I'm gonna say email is best. I'm trying to switch out to.
Cool.
I'll just put my email in the chat.
Sweet, sweet. And we can repeat this again at the end, but awesome. Yeah, let's dive into this diagram. Looks
Cool.
Pretty fun.
So just to talk over the step-by-step process for sending packets. In order from the left to right, if you have some module, can you see my cursor? Hopefully. So module, call it module A. Module A wants to send a packet to module B. Module A and module B, of course, are on two separate chains, chain A and chain B. What does module A do? First, module A constructs the packet. It addresses it correctly. It encodes some data into it. Maybe it wants to transfer tokens, for example. It then passes that packet to the IBC module sitting on blockchain A. The IBC module takes a look at it, says, oh, okay, this packet is basically, parses the address. It says, oh, this packet is destined for blockchain B, looks it up, makes sure it knows how to talk to blockchain B, how to authenticate it. Then the IBC module commits that packet to an outgoing queue. Blockchain A, the consensus algorithm of blockchain A, runs a new round, processes the transaction, comes to consensus on the new value of the outgoing queue. A relayer notices, the relayer has to be watching blockchain A, the relayer notices, oh, there's a new packet. It then figures out where that packet needs to go. It connects to a node of blockchain B. It sends that packet in a transaction to blockchain B. Blockchain B then processes that transaction. It sends that packet to the IBC module. The IBC module parses the packet, authenticates it, makes sure that it was actually sent by blockchain A. It then figures out what module on blockchain B it needs to send the packet to, which is of course module B, because it was addressed to module B. Then module B gets the packet. Module B knows, since it's been processed through the IBC module, the packet actually came from module A, and module B can parse it and perform appropriate state transitions, such as transferring tokens or doing some kind of voting, whatever the application wants. Now, to send a packet in the reverse direction, you just reverse the arrows or reverse the numbers. So if module B wants to send a response back to module A, it can send a packet to the IBC module and module B back through consensus on blockchain B. The relayer will pick it up and relay in the reverse direction. Blockchain A will process the transaction. The IBC module will check the authenticity of the packet, and module A will be able to process it and perform appropriate state transitions. So that was the Tau of IBC, or the core protocol. Now, that is all written. So you can download that code, you can run it, you can interface with it. You're totally welcome to dive in and modify it. But perhaps the most interesting thing to do now is to write application layer protocols. So application layer protocols sit on top of IBC. They describe ways to realize certain sorts of application logic using the primitives provided by IBC. These look a lot like, if you're familiar with Ethereum, these look a lot like ERC standards for token, for not token specifically, but for call data. So call data, of course, is also just a byte string that's passed from contract to contract in Ethereum in the EVM, but it's helpful to standardize particular semantics. So it's helpful to define particular encodings for particular data in call data, say a number of tokens and a destination address, so that all contracts can create and parse it the same way, and analogously for IBC. So what are some examples of applications one might be able to or want to write? First simple one is token transfer. Using IBC, you can transfer tokens from one chain to the other by escrowing them on the source chain, creating basically vouchers on the destination chain, which you can then play with in contracts on the destination chain for as long as you want. And when you're done, you can send them back along the channel to the source chain and get your original tokens back. Cross-chain account abstraction, you might want the ability to keep keys on one chain, but to actually control send transactions on another chain, and you can use cross-chain account abstraction to do this. So you have all of the authentication logic on one chain, but the other chain kind of acts as a slave, I guess, and takes orders from whatever the keys on the first chain tell it to do. So sends whatever transactions or transfers tokens on that chain or anything. Interchain code relocation, this looks a lot like sharding, but it's more general. So you can, of course, packets are just data, and data can contain code, so you can transport code in packets from chain to chain, perhaps to do some sort of load balancing on top of IBC where you want to send code around so that you can minimize the maximum load on any particular shard at any particular time, and you can do this with interchain code relocation. Now, all of the logic for when to send code, how to load balance, which VMs on which chains are capable of running which code is up to you. IBC doesn't prescribe that. It's not a sharding protocol, but it's a set of primitives that can be used and will make the task of building such a sharding protocol much easier, we think. Another quick interlude. Any questions on what the application side looks like? And there are many, I mean, just like there are hundreds and hundreds of ERC specs, those are just a few examples. I'm sure that you and many more people will come up with more examples than I could ever imagine.
I have some questions, but I think I'm going to save them for the end. So I think feel free to keep going if you don't see anything in chat.
Okay, there are just a few more slides, and then I was going to go over the code briefly. Hoping that would be helpful. So just to list the repositories, there are basically 3 repositories that are relevant right now. There are also other implementations in progress, but they're not yet user ready. The IBC specification, IBC is fully specified. You can find that at cosmos/ICS on GitHub as a PDF and as a set of markdown documents. Of course, suggestions or additions are welcome. The Golang SDK implementations, the implementation of the core IBC protocol and of one application protocol, namely token transfer, can be found in the Cosmos SDK in the x/IBC module. And finally, the Golang relayer, which is responsible for relaying packets from one chain to another, can be found at github.com/occlusionally-inc/relayer. So in order to, say, set up an application protocol and start relaying between 2 chains, you would want to create an app, import the IBC module, configure the IBC module to work with your application protocol, start 2 chains, then set up an instance of the relayer to relay between 2 chains. And because the IBC protocol is application agnostic, you can use you shouldn't really need to modify the relayer. So even if you define a new custom packet type the relayer has never heard of, the relayer can just process it as an opaque packet, and you just need to understand it on both ends of your application logic. Does that make sense?
Yep.
Hey, Jack, how's it going? Oh, you muted, sorry. Good to see you. Good morning. Yeah, so I was actually going to...
All right. At the risk of, I don't think trolls are coming in this late. You guys can now unmute if you would like. Let's see if this works.
Hey, Chris, morning. Also, if anyone has any questions while Chris is presenting, I'm happy to answer those in the chat as well.
Thanks, Jack.
So, what would be most useful? What do people want to do? Here are some things I could do. I could walk through the code in the SDK. I could walk through specifically you want to see some code? Okay, cool. Do you want to see the core protocol code, or do you want to see an example application protocol? How to get started? All right, let's take a look then in an example application protocol. I'm going to somehow do this. You can see, ooh, this might be too small. Can I zoom in? Cool. Can you read this?
Yep, I can.
Yep.
It's a little
Cool.
small, but.
It's a little small. I can zoom more. Okay.
Better.
So here we're looking at the 20 transfer module. The 20 transfer module in the Cosmos SDK is the first application level protocol that we've implemented. What's the Cosmos SDK link? Someone else pasted. It's x/IBC/20-transfer. So this is a module. I guess it's a submodule, but you can write any application level protocol submodule using the Cosmos SDK. So it has the normal files you would expect for a module.go, which defines all of the basically requisite boilerplate for application modules. Not too exciting, not too exciting. Then, well, let's do this in a slightly different order. So what's the first thing you need to do when you craft an IBC application level protocol? You need to think about what packets you are sending. So we can find the definitions here in type/packet.go for the 20 transfer module. So if you look at from lines 12 to 16, we see here something called fungible token packet data. And this is just a struct that we defined in Golang, but we are going to encode and decode this struct when we send and receive IBC packets. So here, this specific application protocol is designed to allow transferring tokens from one chain to another, where basically the supply and variance are preserved. So you either have tokens on one chain or you have them on the other chain. And we do this by crafting a packet type and describing some logic for how to send and receive that packet. So first, the packet type. Packet type just consists of an amount, which is this SDK.coins type, so basically a balance and some denomination, sender, and a receiver. You'll notice that the sender and receiver are both strings. This is because address formats can vary between chains. So they're not, usually in the SDK, addresses are SDK.ACK address. And in fact, when you receive a packet, you will need to decode it into an SDK.ACK address. But in the packet itself, we want the packet to be address format agnostic, so they're just strings. This is all you need, in addition to the handler logic. To define a packet, you just need to define a struct. Then there's some helper methods, but that struct will be encoded and decoded when you send messages from one chain to another. We also define, and this is optional, but it will often be useful, we also define an acknowledgement type. And in this case, for the 20 transfer module, we define an acknowledgement type that will allow us to report whether a transfer has succeeded or failed with a Boolean flag, and will allow us to include a arbitrary string as an error message, so that users can figure out if the transfer failed, why it failed. Does that make sense? So that's the packet definition. Now let's go to how we deal with those packets. So there are two sides to, there's always a send side and a receive side. And I think, yeah. So the send side here is in a function called create outgoing packet. And create outgoing packet is called when a user sends a transaction. So in the case of the 20 transfer spec, at least at the moment, everything is initiated by some user sending a transaction. So a user sends a transaction to chain A that says that they want to send coins to chain B. So when they send that transaction, I'm not going to go over that part because it's just standard Cosmos SDK stuff. When they send that transaction, the keeper gets called, then create outgoing packet gets called. And create outgoing packet is going to do two things atomically. It is going to escrow the tokens, and it is going to craft and commit the packet the user wants to send to chain B. So basically, the first part of this logic here is for dealing with escrowing, for escrowing the tokens from the user who's sending to this module. They'll be stored temporarily in the module account. And then we craft this packet data using the packet type that we just defined, the fungible token packet data. We craft the new packet, we address it to where the user wants it to go, and we include some other fields for a timeout, just sort of control stuff. And then we call send packet. So send packet is a method on the IBC keeper. That's cool. GitHub always has new features now, ever since they got acquired by Microsoft. Whenever I go to it, I didn't know I had this thing. This is super cool. So send packet is a function defined in the IBC keeper, which commits the packet to an outgoing queue. And now it is essential that this logic is atomic. What do I mean by atomic? I mean that as the Cosmos SDK already has provisions for, either the tokens get escrowed and the packet gets sent, or neither happens. If you only escrowed the tokens but didn't send the packet, then you might lock up the tokens forever. And if you sent the packet without escrowing the tokens, then you would be able to mint tokens. So we want this to be atomic. Luckily, the Cosmos SDK is already designed for that, so we can just use the standard transaction semantics. And if anything fails, the whole state transition will be reverted. That is the send side. So that's the logic that deals with sending a packet. So we've escrowed tokens, we've crafted this packet, we've committed this packet to the outgoing queue. Now let's talk about the receive side, which is just below. So in on receive packet, now think about it, we're on the other chain, say chain B, the receiving chain. Packet has been sent, we've got the packet. By the time this function gets called, the packet has already been authenticated. So the IBC keeper handles all of the authentication logic for you, handles all of the sort of not user account address, but module address parsing logic, and gets the packet to the right module. Now we've got this packet and we need to handle it. So we do a little bit of validation here because at the moment you can only send one denomination at once. Now we decode the receiver address, we make sure that we can actually send coins to this account. And then based on whether or not we're the source chain, and I'll tell you what that means in a second, we either mint coins or we unescrow coins to the receiver. So if you think about what's happening in sort of the context of both of these transactions, a user sends a transaction to chain A, tokens get escrowed, a packet gets committed to the outgoing queue, relayer, so in between, there's a bunch of magic happening. Basically, the relayer is picking up the packet, it's relaying it from chain A to chain B. So now this code is running on chain B, and chain B picks up the packet and says, oh, okay, now I need to handle this packet, and this packet contains some tokens, so I'm going to send those tokens to whatever the packet said was the receiver. So if you think about what happened across both of these chains, tokens were escrowed on one chain and tokens were minted on another chain. So the total amount of supply remains constant. And because all of these packet handling actions are atomic, either the packet gets sent and it can be received, or it doesn't get sent and tokens were never escrowed. So you never lose tokens or mint tokens out of nowhere. They're conserved. And that's what you want, of course, to have a useful currency. Does that make sense? Send and receive sides. Any questions on those?
Yes, sir. Makes sense to me.
Cool. Shall I go over acknowledgements briefly? So think about what happens if blockchain B is really, really busy. So blockchain A succeeds. Blockchain A calls create outgoing packet. The packet is created, tokens are escrowed. But blockchain B, maybe blockchain B is Ethereum, and a new dApp has just been launched. CryptoKitties Redux, crypto COVID. I don't know. And that new dApp is, of course, drawing lots of transactions. So now it's not possible to confirm the packet on blockchain B because there's just too much transaction volume. There's not enough gas. And many blocks go by, the packet still isn't confirmed. What happens? So a little bit of this is up to the application, but what we want is for the atomicity to be preserved, for it to be the case that the user can either get their tokens on chain B or they can get them back on chain A. And in order to achieve that, we include in packets a timeout field. The timeout can be specified either as a height, so a block height, or as a timestamp. And the way the timeout field works is that when the timeout has passed on blockchain B, which happens independently of processing the packet, because it's just related to the height of the timestamp, the packet can no longer be received on blockchain B, but it can be timed out on blockchain A. And for it to be timed out on blockchain A simply means that blockchain A can say, oh, look, blockchain B never received this packet. The height has passed, it's too busy, it won't ever be able to receive this packet. So I can safely revert whatever state transition I did when I created the packet. So in the case of sending tokens, reverting the state transition just means refunding the tokens. Now again, the IBC core modules handle all of the complex logic for you. So all you need to do is define this function called onAcknowledgement packet. An acknowledgement packet, in the case of token transfer, simply says, oh, look, oops, sorry, on timeout packet, they actually do the same thing, but I'll get to that in a second. On timeout packet, in the case of token transfer, says, oh, the packet timed out. They can never be received. The tokens can never be claimed on chain B, so I'm just going to refund them. So if your packet never gets its way to chain B, eventually it will time out. You can call on timeout packet, and you will be able to get the tokens back unescrowed on chain A. So that way, again, tokens are conserved, even in the case where blockchain B is moving too slowly or too busy and can't process the packet. Do timeouts make sense? I'll take that as a yes. Finally, acknowledgements. Another problem might happen. What if the receiver address is not understood? What if it's not an account? What if it's wrong? What if, for whatever reason, it can't accept coins? We want to deal with that case too. So in that case, blockchain B is processing the packet, but something about the packet is wrong. The user didn't craft it correctly. They typed the wrong address. It can't be understood. Who knows? But we want to be able to handle that case again, handle it in a way that will allow us to preserve conservation of token supply, so refunding the tokens on chain A. And we do this by defining an acknowledgement type. So I'm going to go back quickly to the types file just to refresh. So remember, we talked about the fungible token packet data. We already went over the send and receive logic for that. Then the second type defined in this file is called the fungible token packet acknowledgement. And this is what blockchain B can send when it receives a packet. As basically a little bit of data back, blockchain A can then process and react to. And a fungible token packet acknowledgement just contains a Boolean describing whether or not the transfer succeeded, and a error message, which can be any arbitrary string. So if we go back to the keeper logic here, if we look at blah, 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 on acknowledgement packet, all on acknowledgement packet needs to do is check if the transfer succeeded, and if the transfer succeeded, do nothing. If the transfer failed, refund the tokens. So if the receiving account on blockchain B was, for whatever reason, we don't really care, was unable to receive tokens, then we need to refund them so that supply will be conserved. That's all with respect to acknowledgements. Any questions on that basic logic?
Nope.
So some other parts that you might want to implement, just to go through them quickly. If you're implementing an application level protocol, you will want to implement some actual messages that your users can send transactions. Some of those transactions will trigger IBC packets. So here we have message transfer. So this is what a user sends when they want to send packets, send tokens using IBC packets from one chain to another chain. Any other messages? No, just this one. And you'll see that this specifies some address information. So it specifies basically which other chain these tokens need to be sent to. Then let's see, what else might you need to define? Just some other boilerplate, blah, blah. I don't think we need to go over any of this. Events, you want to see events? Sure. I think these are just some events which are logged when packets are sent and received. And we're just defining some constants.
Just a quick note, if folks want to see events, the relayer has a way to listen to whichever chains that it's configured to and just print all the events to standard out. You can filter by block or transaction events. So if you want to explore which events IBC kicks out, that's a great way to do it.
Great, thanks. Yes, this just uses the event system in the Cosmos SDK. So the IBC module itself logs a bunch of events, which you can see if you run the relayer with the verbose mode, as Jack mentioned, and you can also define events in your own application level protocol that log whatever you want. So just to quickly go through the functionality of message transfer. So if we look at, oops, if we look at handler.go, handler.go is what we'll deal with, the incoming message. So this is a user transaction, message transfer, and then it will call send transfer, which is going to send the IBC packet, and then it will also log an event. So the other part I want to cover briefly here, and it's a little bit more advanced, you can probably just copy the default from this module if you are not interested in using it in any fancy way yet, but is the handshake callbacks. So remember from the earlier presentation, I talked about handshakes and connections and channels for IBC. And in the case of channels, handshakes can be hooked into by the modules. So handshakes are by default completely public. So any other module on any other chain can try to open a channel to your module. And oftentimes you're not going to want them to. Just like oftentimes when someone hits your web server, they're going to be speaking the wrong protocol, or they're going to be a blacklisted IP, or they're some rando you don't know, and you don't want to open any sort of channel to them. Now, in order to allow modules their customization over that logic, the IBC core modules provide basically a set of callbacks that modules can implement. These are called on-chan open init, on-chan open try, on-chan open ack, and on-chan open confirm. And you'll see here that in the 20 transfer module, we're basically just doing a bunch of validation logic. We're checking if the other module is talking on the right port, the port that we expect. We're checking if it's speaking the right version of the protocol. We're doing some stuff here related to capabilities so that we can own the channel. We are checking the same thing on the other side. That's basically it. You can also do state logic in these callbacks if you need to. So if you need to associate a particular bit of code with a particular channel, or if you need to create a new address to handle escrow for a particular channel, you can do all of that in these callbacks. Channels can also be closed by either party. And if you want to prevent channels from being closed, which often you want to prevent, you can just return an error from the appropriate callback. So an appropriate difference worth emphasizing, say from TCP/IP, is that connections and channels in IBC are intended to live essentially forever, modular chain upgrades or hard forks. So once you create a connection between two chains, once you create a channel between two modules, it doesn't, the channel, it's packets time out, but the channel itself does not, in most cases, need to time out. It can just keep going. So you don't need to create a new channel like every time you use IBC. It's not like a session. It's not like a TCP socket. It's designed to be persistent. And since the blockchains themselves are, generally quite fault tolerant and reliable and continuing to run, in practice, we expect this to work reasonably well. Now, of course, if you could perhaps, a channel could completely time out, or you could decide that you want to use a new one, and you can always create one. It's not too expensive. It just requires another handshake. But for the most part, you should not need to. That's basically it. That's about all you need to do to define a custom IBC application protocol. You can copy the code, if you like, from this 20 transfer. There are also some documents in somewhere. There's some docs, in addition to the full IBC protocol spec is very detailed and covers the core protocol, which you might not care so much about yet. But if you just want to learn about what is where, which is what is where in the code, you can go to the spec folder in x/IBC and read through these brief markdown documents which talk about that. There's particularly a spec for the fungible token transfer, which describes what it's doing. Oh, I guess that just links to the spec, but you can read that part of the spec. And there are some relevant ADRs if you're curious about how some of this logic was designed in the SDK.
Awesome, Chris. Thank you so much for that, man. That was awesome. And I know some of the devs in the chat who are actually working on these challenges really appreciated it. You guys are able to unmute right now if anyone has any final questions. I like to live slightly dangerously. But if there aren't, I guess just from my perspective, in a bigger picture, Chris, like what are some things, some examples that are things like possible to build on Cosmos now that may have been difficult before, and any specific pieces of infrastructure that you'd like to see built, soon, or maybe in this hackathon?
Yeah. So I think one of the primary advantages of a heterogeneous interoperability protocol like IBC is that it can allow state machines to specialize. So it can allow one blockchain to be good at doing one thing and another blockchain to be good at doing another thing. And then you can communicate between the two blockchains when you need to. So for example, right now, there are only a few blockchains which are very good at doing private transactions. In fact, there's really only one at the moment, Zcash. And all other, perhaps I risked some ire, but from any reasonable objective standard, all of the privacy solutions are just worse. So, but it's hard. Like it required the Zcash team of cryptographers to develop a custom circuit. It required them to deploy this blockchain. It took years. But right now, no one else can use it. Like you have to use Zcash, which as a blockchain is maybe not what you want, or you want smart contracts, you want different assets, etc. So I think connecting, maybe potentially Zcash specifically, but also just connecting a shielded circuit of the kind which Zcash has implemented to a chain which supports IBC would then allow a lot of assets to instantly make use of that shielded circuit. So that's one use case I think is particularly compelling. Another related to sort of Cosmos specifically use case that I think is compelling is what we call cross-chain validation, or in the same category of protocols as I think Polkadot calls shared security, which is partial sharing of validator sets across chains. So a way in which you can basically contract with the validators of another chain to validate your chain in exchange for some payment, negotiate that automatically over IBC, and suddenly get new validators and more collateral securing your chain. That will make it much easier to spin up zones. Right now, it's still, and by zone, I just mean, at a very high level, a blockchain which speaks IBC. Anything can be a zone. Right now, in order to spin up a zone, you need to recruit a validator set, which is tricky. It takes months. You need to find high quality validators or your zone won't be secure. And that cost of entry could be drastically reduced if it were possible to basically use a protocol to match validators who are providing security and zones who are paying for security. And that can be implemented over IBC. And you can implement all of the parts you need for security, like slashing over IBC. So that would be a second use case that I think is pretty exciting. Maybe a third use case is contract migration. So like I mentioned, since IBC is completely protocol agnostic, you could send code over it too, although this 20 transfer example doesn't do that. But say you have some popular dApp running on Ethereum, running on some other chain that supports the EVM, and the chain gets too crowded and it starts to get too expensive to use your dApp. You could simply move it and move state. This requires a little bit of architecture design, but it's possible in principle. You can move the code and move the state to another chain, potentially forever, potentially temporarily, just while the load is high. You could process transactions on another chain, and when you're done, when the load is lower, or maybe you never move, but if you want, you could move back. So that would be some kind of interchain code relocation alongside load balancing. Maybe the load balancing is custom, maybe you're doing it by hand, or maybe it's eventually it becomes automatic. And I think that's another use case, and I think it's one which benefits from the heterogeneity of chains supporting IBC. Some chains are going to be good at some things, some are going to be good at other things. Storage and compute costs will vary, VM support will vary, and different dApps have really different preferences. Some dApps just don't need or don't really benefit from the security. Like the security of something like Maker is not actually the security of Ethereum, it's the security of the signer set of the Oracle keys, so of the price Oracle keys. So in a sense, Maker is paying for a bunch of security by running on Ethereum, which it doesn't get. Like it's security is always the lowest common denominator. So hopefully IBC can make it easier to pay for the security you actually want to need.
Interesting. Yeah, that's a really good point.
All right, I think we're approaching the hour.
We are indeed. And so I just want to say before people start hopping off, we do have office hours coming up in 1 minute with the Cosmos team. I don't believe you'll be on there, right, Chris? But I think Peter, you're on here. You'll be in there?
Yeah, I'll be on there with Marco.
Perfect.
I can jump on too.
Thanks, Jack.
Sweet. Yeah. So I'm not sure if we'll need the full hour, but it'll be on a slightly different Zoom link. Everyone in here should have it on their calendar, but we'll just hop in there in a moment. But Chris, thank you so much, man. This was awesome and super helpful, I think, for everyone, me included. Anything you want to say before we all hop off to the other link?
Just that I look forward to seeing what everyone builds with IBC. We've spent lots of time, in our cathedral building the protocol, but now the most exciting part is to see it in practice. Feel free to email me anytime if you have questions.
Awesome, man. Yeah, the email is in the chat. I'll just take it and repost it right now, but this video will also be on YouTube hopefully by tonight. So keep an eye out for that. If you missed anything or if you want to reference it, come check it out. And thanks everyone for attending.
Thanks. Ciao.
Thank you,
Bye,
Chris.
Yeah, thanks so much.